Right. I got problem 9.12. It says the expressions for the steady state voltage and current at the terminals of the circuit seen in figure 9.12 are there's a function for the voltage and there's a function for the current. And the current, we notice it's in sine, so we'll eventually have to turn it into cosine, but we'll get to that. So the first question is asking, oops. So the first question is asking, what is the impedance by the source? So impedance follows the same rule as Ohm's law, right? V equals I Z. We can think about it as that way, right? So ZG is going to be equal to VG over IG, correct? So we can go ahead and format it this way. 300 cosine 5,000 PT plus 75 degrees over 6 sine 5,000 PT plus 123. So we really can't, so you want to convert this sine to cosine. So I think that would be one of the addition, one of the trigonometric identities that says that it's a sine of x, I believe, is cosine of x minus 90. So we go ahead and, oops, let's do that. Yeah, so we go ahead and do that. 300 cosine 5,000 PT plus 78 degrees. And we go 6 cosine of 5,000 PT plus 123 minus 90, which would be 300 cosine, snugly S, 5,000 PT plus 78 over 6 cosine 123 minus 5,000 PT plus it's 33 degrees. So then we want to transform these two into different forms, right? So we want to convert these into phasor domain, both into phasor domain. So we know that 300 e to 78 j over, it's going to be, well, we follow this format. Actually, let me write that down because what I'm just saying doesn't make sense. So we know the phasor domain form of V cosine plus is going to be equal to right. Okay, so if that makes more sense following that notation, or following this is what I'm following to convert these. So 3e to the 33j, right? And this is all equal to the impedance, CG. So, oh, it's not 66, it's 6, right? So then, yeah, 300 over 6 would be 50. 50e to 78 minus 33j. 50e, and that would be, I think, 45. Yeah, 45j. Okay. So this would be the function of impedance, and we can go ahead and transform this. dg is going to be equal to 50 cosine 5,000 pt plus 45 degrees. That doesn't, just to make it pretty and make it legible. That makes sense. All right. And so now it's asking by how many microseconds is the current out of phase with the voltage, right? So we know our angular frequency is 5,000. I think what it means by P here is pi. I think from the book, or I'm going to assume that. So by how many? Yeah. So we know the angular frequency, so we know that T equals 1 over F, and that equals to 2 pi over the angular frequency. So we can go ahead and first solve for our frequency, and then we can solve for the period. And using our value for the period, we can find how much it lags by. Right. So so we know frequency off this. We know that it's going to be so let's solve for this. Pi over 5,000. Okay, so frequency is 2,500 hertz. So then we can find that our period is 1 over 2,500, right? And it's 1 over 2,500. Calculator 1 over 2,500 is 4 times 10 to the negative 4. So I'm going to say 4e to the negative 4 seconds. So the question is how many microseconds the current out of phase with the voltage. So if IG lags VG, then we know 45 over 360 times 4e to the negative 4 seconds is how much it lags by. So 45 over 360 times 4e to the negative 4 is going to be 5e to the negative 5 seconds. And that's going to be 5 times 10 to the negative 5 seconds. And that would be our answer for 9.12.